We live in a digital world, but what does that really mean? In this lesson, we're going to look at analog and digital and try to decide which one really is best. We'll look at logic gates and then try to build them into something more useful in logic circuits. And if we wanted to, we could then move on to Intel and ARM chips that you have in your computing devices and phones. But maybe not today. What we'll look at today is we're going to start with the basics, and let's look at analog and digital to start off with. These two graphs here show very clearly, to me at least, the difference between the two. Digital means the information is split into discrete bits. Think of it like integers, 1, 2, 3, 4, 5. Analog can take any value, 2.357 for example. That makes analog much better really, because if you want to record a song, for example, don't you want to have as much of the song as possible? Why do you want to turn this into this? Well, I suppose it's retro, but we're losing something. But there are a few reasons why we might want to go to digital, including being able to repair digital files, saving disk space, and making it easier for computers, so they don't need to be so powerful. That's where we come in, because we are learning about the basics of electronics. In electronics, we work with ones and zeros, highs and lows, ons and offs, although let's stick with highs and lows. It's simple, as we don't need to worry about something being a little bit high or nearly low. It's either high or low. That simplicity gives us power, because it lets us combine highs and lows together in interesting ways and build things like calculators and computers. Let's look at 5 logic gates and see what they do. Later, we will see how we can combine these together to make useful circuits. These are the 5 logic gates we need to cover. So the first thing is to know what they are and how to draw their circuit symbols. The first is a NOT gate. It's the most basic, as it only has one input and one output. All it does is change a low into a high or a high into a low. It's just a triangle, but the significant part is that circle. That's a clue we'll come back to. Second is the OR gate. This has 2 inputs and 1 output. If input A or input B is high, the output is high. Third, the AND gate takes the 2 inputs. If A and B are both high, the output is high. The last two, NOR and NAND, are a little more complicated. I'm going to draw an OR, like before, but I'm going to add a little circle this time, just like we had on the NOT gate. That means it is OR followed by NOT. It probably should be called an ORN or ORNT gate or something like that, but NOR just sounds better. NAND follows the same idea, an AND gate followed by the circle to show it has a NOT after it. I'll come to those two later on to show their behavior, but it's easiest if we look at it in a table. This is a truth table. Its purpose is just to tell us what happens when we put high and low inputs into our gate, or series of gates. Starting with a NOT gate, do you remember the circuit symbol? There was only one input, one output. Hopefully you remember that. If the input is not high, the output is high. So if input is 1, the output is 0. If the input is 0, the output is 1. The NOT gate is also called an inverter. OR gate. What was the symbol? The back end curves in, and the front goes to almost a point. Like most gates, it takes 2 inputs, so the truth tables are more complicated. We now have 3 columns because there are 2 inputs and 1 output. We also need more rows because there are more possible combinations for the inputs. It can get tricky keeping it organized and not repeating yourself or missing something, so I suggest you follow the same pattern every time. Here's the pattern I use. Start with 0, 0, so both inputs are low. Ignore the output column for now. Now 0, 1, so I'm starting on the right just like I would when counting numbers. Next is 1, 0, then 1, 1. Look at the table. It looks like I've written 0 at the top, then 1, 10, 11. All the numbers are going up in order. Now for the output column. It's an OR gate, remember, so 0 or 0 is low. So I write 0 there. 0 or 1 is going to be 1. 1 or 0 is 1, and 1 and 1 is 1. With an OR gate, having both inputs high is as good as only one being high. The AND gate is next. Looking a little like the OR gate. Try sketching one. It has a flat back and straight edges before the curve. Let's draw the same starting point with the inputs. 0, 0, 0, 1, 1, 0, 1, 1. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. So the output is only high if input A and input B are both high. NAND gate. Remember I said it was an AND followed by a NOT gate? Well, that means the easiest way to solve this truth table is to think of it as two gates. So I'm going to squeeze in an extra column here. Now I'll fill in my inputs. Next, complete the truth table for an AND gate. 0 and 0, 0 and 1, 1 and 0, 1 and 1. And finally, take this column as the input for a NOT gate, giving us 1, 1, 1, 0, inverting the output. Obviously, you could just remember that rather than write it out. And I'm going to rub out my working now. Okay, don't normally rub out your working, try to show it, but I want my truth table to be final and complete. Last, it's the NOR gate, drawn like an OR gate with a circle on the nose. Fill in my inputs. 0 or 0 is 0, NOT makes it 1. 0 or 1 is 1, NOT makes it 0. 1 or 0 is 1, NOT makes it 0. 1 or 1 is 1, NOT makes it 0. That's it for the logic gates, but we're not done yet. We should be making this more useful, and we're going to do that by combining our logic gates into a full circuit. I've drawn one here already. Let's think about what it does. The full circuit to make this is quite complicated, so we're just going to use this logic part and imagine we have some sensors as well. What do I mean by sensors? Can you think of something we could use to sense the surrounding environment? The ones that we're going to work with are thermistors, LDRs, and simple variable resistors. We've already seen these and how these can be used in potential dividers to control the potential to make it high or low. We could even just take the output from a switch, on, off, high, low. So imagine how we could take that output and feed it into one of these. Let's say we have a thermistor controlling input A, and a switch for input B, and let's see, a light dependent resistor for input C. What's going to happen? Let's find out with a truth table. This time there are 3 inputs, so we need more rows. Fill in the inputs with a pattern so we don't miss anything. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then put ones at the front. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 8 rows, all different. We're ready. The output is Y. That's quite a jump to get all the way there. So let's add D and E to the diagram and to the table. We have a NAND, a NOT, an AND, and neither an OR nor a NOR. We want to consider input A NAND input B. 001, 001, 010, and so on. If you can't keep up, you just need to practice some more. Then we have C NOT. So that's 01, 10, 01, 10, 01, 10, 01, 10. And finally, we have D and E. So 1 and 1 is 1, 1 and 0 is 0, 0 and anything is going to be 0, so I can just fill in the rest. So what does this do? I'm going to add some little indicators onto the table to help me keep track. This is not that hard, but it does need some good mental organization sometimes. Let's say a hot thermistor has low resistance, so voltage would be low. Remember, V equals IR, so low resistance means low voltage. So I'll highlight the hot conditions red, like so. The switch is obvious. 1 means on normally. The LDR, like the thermistor, if it has lots of energy, like in this case, resistance is low. So I'll indicate the zeros with a yellow highlighter. Finally, I'm going to put a light bulb on the output so I can see what's going on. From the table then, if it is hot and the switch is closed and the light is bright, the bulb will come on. In the second row, it's hot and the switch is on and it's dark, so the bulb does not come on. And in this example, that's about all there is. That was a lot to take in. So you might need to review that, make some notes, draw some truth tables, practice drawing the diagrams, the circuit symbols, so that everything just becomes automatic for you. We've looked at analog and digital earlier on. We've looked at different kinds of circuit symbols. So we have logic gates, and then we built them into something useful, into a logic circuit. So we now have an idea of how to make something that will actually trigger based on the environment around it. We've now got something useful. We've got the basics of a computer, and with a bit more understanding, we'll be able to make our circuits do even more, so that they become even more intelligent. This is the technology that your computers are built on, and it just gets more fascinating the deeper you get into it.